At this stage, you have enough background to talk about a concept that quietly sits underneath many modern security uses of artificial intelligence, AI, and that concept is embeddings. Embeddings are one of those ideas that can sound mysterious until you realize they are simply a way to turn meaning into numbers so a computer can compare things that do not match word for word. In security, comparisons matter because we are constantly trying to decide whether one event resembles another, whether one message resembles known malicious content, or whether one user request resembles something risky. Embeddings make those comparisons faster and more flexible, which is why they show up in search, classification support, and systems that retrieve relevant information for a model. The downside is that embeddings can carry traces of what they represent, and those traces can become leakage paths if you treat embeddings like harmless metadata. By the end of this episode, you should be able to explain what embeddings are, how similarity search works, what semantic space means, and why defenders worry about leakage. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. An embedding is a vector, meaning a list of numbers, that represents an item such as a piece of text, an image, or even a user behavior profile in a way that captures important patterns. The key idea is that the numbers are not random. They are learned so that items with similar meaning end up with similar vectors. If two sentences mean roughly the same thing but use different words, their embeddings should be close to each other, while sentences with very different meaning should be farther apart. This is extremely useful in security because attackers rarely repeat the exact same wording, and defenders often need to recognize variations of a pattern. Embeddings can be produced by models trained for language understanding, often connected to the field of natural language processing, NLP, and the output is a compact representation of meaning. A beginner misunderstanding is thinking embeddings are a code that can be read like a dictionary, but they are more like coordinates that only become useful when you compare them. The comparison is where the magic and the risk both live. To make this concrete, imagine you have 1,000 incident summaries written by different analysts over several years, and you want to find which past incidents resemble a new one. Keyword search will miss matches if wording differs, and it can overmatch on common words that are not actually meaningful. Embeddings allow you to represent each summary as a vector and then ask which vectors are closest to the new summary's vector. In practice, this means the system can retrieve relevant past cases even when the words don't match perfectly, because the embedding captures the underlying semantic pattern. For a defender, this can speed up triage and improve consistency, because it surfaces the closest known patterns instead of forcing a human to remember everything. The high-level mechanism is still simple. Turn items into vectors, compute closeness, and return the nearest neighbors. The security concern is that the embedding is derived from the text, and if the text includes sensitive details, the embedding becomes a transformed but still informative artifact. Transformed does not mean safe by default. Similarity search is the process of using embeddings to find items that are close to each other in the vector space. Closeness is typically measured with a similarity metric, which is just a way to compute how aligned two vectors are. You do not need the math for the exam, but you do need the intuition. If two embeddings point in nearly the same direction, the items are semantically similar. If they point in different directions, the items are less related. Similarity search is powerful because it supports fuzzy matching of meaning rather than exact matching of strings. For security use cases, that can mean finding related phishing messages, grouping similar alert narratives, identifying recurring attacker patterns across different logs, or linking user requests to known risky categories. The beginner trap is to treat similarity as truth, when similarity is only a clue. A system might retrieve items that are close in meaning but still different in a security-critical way, such as matching a benign administrative script to a malicious one because both mention similar operations. Defenders must treat similarity search as a prioritization tool that feeds investigation, not as a final verdict. When people say semantic space, they are describing the geometric world where these embeddings live. In semantic space, each item is a point, and distance corresponds to meaning as learned by the embedding model. This space is not hand-designed. It emerges from training on large collections of data where the model learns which patterns tend to appear together. The result is a space where clusters can form, with items about authentication near each other, items about malware behavior near each other, and so on, even if phrasing varies. For security, semantic space helps because it provides a way to organize and search knowledge that is messy, inconsistent, and high volume. It also creates a new mental model for defenders. Instead of thinking only in keywords, you can think in neighborhoods of meaning. A misunderstanding here is thinking the semantic space is objective reality, when it is actually a learned representation with biases. If the training data overrepresents certain patterns or language styles, the space will reflect that, which can affect what gets retrieved and what gets missed. One place embeddings show up is in systems that assist analysts by retrieving relevant context for a question. If an analyst asks for policies related to a type of incident, the system can embed the question, search for similar embedded documents, and return the closest matches. The analyst then uses those documents to make decisions or to write accurate responses. In a learning context, this seems like a straightforward efficiency gain, but in security, it changes the threat surface. The retrieval step depends on what documents are embedded, how they are segmented, and what access rules govern which embeddings can be searched. If embeddings for confidential documents are searchable by a broad audience, the system may reveal sensitive information indirectly by returning related content. This is why embeddings are not just a data science artifact. They are part of an access control boundary. A good defender asks whether the retrieval system respects role-based access and whether it can leak information across boundaries. The safest posture is to treat embeddings and their indices as sensitive assets when they represent sensitive data. Leakage risks can feel counterintuitive because embeddings are not readable text, but leakage is not limited to dumping raw strings. Leakage can be about revealing that a concept exists, revealing relationships, or enabling inference. If a user can query an embedding system repeatedly, they might learn whether certain internal projects, customers, or incidents exist based on what content is retrieved or how close matches behave. They might also be able to reconstruct sensitive themes, even if they cannot reconstruct exact sentences. This is similar to how metadata can be sensitive even when content is encrypted because patterns still reveal information. Another leakage risk is membership inference, which is the idea that an attacker can sometimes determine whether a particular item was included in the embedded dataset based on responses and similarity behavior. You do not need to memorize that term, but you should recognize the risk pattern. Repeated queries plus informative outputs can reveal what's inside. Defenders manage this risk with strong access control, query controls, logging, and careful decisions about what data is allowed into embedding stores. A particularly common misunderstanding is that embeddings are anonymized because they are numbers, so teams feel comfortable storing them broadly or sharing them between systems. In practice, the embedding is a representation of the original content, and representations can still contain signals that correlate with sensitive attributes. If the embedded text includes personally identifiable information, PII, secrets, or internal identifiers, the embedding may encode enough structure that an attacker can infer aspects of that content or at least infer its presence. Even if direct reconstruction is difficult, defenders should not rely on difficulty as a control. Difficulty is not a policy, and it changes over time as techniques improve. The safe approach is to minimize sensitive content before embedding when possible, and to restrict access to embeddings as if they were sensitive derivatives. Another misunderstanding is to assume that if you control the original documents, you have controlled the embeddings, but the embedding store becomes its own data repository with its own access paths. Treating it as a first-class data asset is part of mature governance. Embeddings also interact with the adversarial nature of security because attackers can attempt to manipulate similarity search. If an attacker can influence what gets embedded, such as by injecting crafted text into logs, tickets, or knowledge bases, they can influence retrieval results later. This can cause a system to retrieve misleading context or to prioritize attacker-controlled content that steers decisions in unsafe directions. Even in a purely internal environment, poison content can spread if the embedding store is used as a shared memory for many workflows. Another angle is query manipulation, where an attacker crafts queries to pull back the most sensitive or revealing content. This is not magic. It is the same principle as probing any search system, except now you're probing meaning-based retrieval rather than keyword matching. Defenders respond by protecting ingestion pipelines, validating content sources, limiting who can add data, and monitoring retrieval patterns for abuse. The exam will reward you for seeing retrieval as a security-relevant interface rather than a neutral convenience feature. Similarity search also has failure modes that look like ordinary errors but carry security consequences. One failure mode is false similarity, where the system retrieves something that feels related but is not actually applicable, leading a user to apply the wrong policy or draw the wrong conclusion. Another is missed similarity, where a truly relevant item is not retrieved because the embedding model did not capture the nuance that mattered, such as the difference between a test environment and production or between internal and external access. These failures can cause bad decisions, like under-responding to an incident or oversharing information. A defender manages these risks by designing workflows that treat retrieved items as suggestions rather than as authoritative sources, and by encouraging verification against primary evidence. Another mitigation is to evaluate retrieval quality using realistic security scenarios, including edge cases and adversarial-like phrasing, because that reveals where semantic space fails to capture critical distinctions. For Security AI+, it's important to remember that embeddings improve search, but they do not replace reasoning. They shift where errors occur, and defenders must be ready for that shift. There is also a lifecycle dimension to embeddings that connects to drift and maintenance. If the organization's language evolves, like new product names, new threat categories, or new policy terminology, embeddings created from older content may not align well with current queries. The semantic space can become stale if the embedding model or the embedded corpus does not reflect current reality. That means retrieval performance can degrade quietly over time, which is similar to drift in prediction models. A defender's posture is to monitor retrieval behavior, such as whether users are consistently finding what they need, whether irrelevant results are rising, and whether certain sensitive categories are being surfaced more often than expected. Updating embeddings or the underlying embedding model can improve relevance, but it also introduces change risk because the meaning geometry can shift and create new leakage patterns. This is why versioning, controlled updates, and revalidation matter in embedding systems too. They are not static archives. They are living components of the security environment. Access control deserves special attention because embeddings can cross boundaries in subtle ways. If you have a document that only a small group should read, and its embedding is searchable by a broader group, the broader group may not read the document directly, but they could still get related fragments returned or learn sensitive relationships. The safe design principle is that access restrictions on source content should follow the content into the embedding store and retrieval layer. In mature systems, retrieval should respect role and identity, and results should be filtered so users only receive what they are authorized to see. This is the same philosophy as an access control list, ACL, which defines who can access what, but applied to semantic retrieval rather than file reading. Another governance issue is auditing, because semantic search can be a powerful reconnaissance tool if misused. Logging queries, monitoring unusual patterns, and setting limits on high-risk query behavior are common defensive strategies. The test will often prefer answers that treat embedding stores as sensitive systems requiring controls, rather than as harmless performance optimizations. Because embeddings are about meaning, they can also amplify the impact of mistakes in data classification. If a document is misclassified as non-sensitive and is embedded into a broadly searchable store, it can be exposed in retrieval results even if no one intentionally shared it. This is a classic security lesson. Classification errors tend to propagate. Embeddings can make propagation faster because retrieval makes content easier to find and reuse. Another issue is that embeddings can connect documents that were previously siloed, which can be beneficial for productivity but risky for confidentiality. For example, a query about an incident might retrieve documents from another team that reveal internal architecture or defensive procedures. Even if each document was individually accessible, the combination can reveal more than intended, which is a form of aggregation risk. Defenders manage aggregation risk by limiting what can be retrieved together, limiting context breadth, and applying additional checks when queries touch sensitive topics. Embeddings do not create new secrets, but they can make existing secrets easier to discover if boundaries are weak. A calm way to summarize the security posture is to treat embeddings as derived sensitive data when the source data is sensitive, and to treat similarity search as a capability that can be abused like any other queryable interface. That means you control ingestion, because what goes in determines what can come out. You control access, because retrieval is a form of reading even if it doesn't look like it. You control output, because returned content can expose sensitive details directly or indirectly. You monitor behavior, because repeated queries can reveal patterns that a single query would not. Beginners sometimes expect one control to solve this, like filtering a few keywords, but meaning-based systems require layered defenses because attackers can phrase the same intent many ways. The exam will favor answers that reflect layered thinking and governance rather than single-point fixes. Embeddings are powerful, and power always comes with the need for boundaries. The most important connection to carry forward is that embeddings are a bridge between raw content and decision-making systems, and bridges must be defended. Similarity search is how that bridge moves information. Semantic space is the map that organizes what feels related, and leakage risk is the reminder that movement and organization can expose things you didn't intend to expose. If you can explain embeddings as numerical meaning coordinates, you can explain why retrieval can find related content without matching exact words. If you can explain semantic space as neighborhoods of meaning, you can explain why systems can cluster incidents and policies even with varied wording. If you can explain leakage as inference and aggregation, you can explain why embeddings need access control and monitoring. That combination is exactly what Security AI Plus is building toward. Not just knowing AI terms, but translating them into security decisions that respect real-world threat behavior. When you approach embeddings with that defender mindset, you can enjoy their usefulness without being surprised by their risks.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.